In this video, we're going to take a look at mathematical proof. Now, this video is more of a follow-on from what we did in GCSE Maths for proof. The next video is where we take a look at the more complicated stuff. So in the next video, we take a look at methods of proof. So to start with, let's just take a look at these two examples here together. So what I want to do here is prove that this quadratic is positive for all values of x. Now, where can I begin with this? Well, let's just think about this quadratic here. So it's going to have a U shape. Okay, it's a positive quadratic. And what we're saying here is that if this is positive for all values of x, then this quadratic here will always be above the x-axis. Okay, might look say something like that. Okay, and notice it's always above the x-axis. So if I can find the minimum point of this quadratic here, then if we can show that that's got a positive y-coordinate, in that case, it must be positive for all values of x. So let's start by completing the square here. So we're quite confident now with completing the square, so that's going to give me x minus 1 all squared. We square this value and subtract it, so that would be minus 1, and don't forget the plus 5 there. So simplify here, I get x minus 1 all squared, minus 1 plus 5, that would give me plus over there. Okay, now from here we can deduce the turning point. In this case it would be a minimum point, so therefore the minimum point, here, that will be equal. So the x coordinate is the opposite to this, so this is minus 1, my x coordinate here will be positive 1. And for the y coordinate here, this will be positive 4. So for my minimum point, I get 1, 4. Okay, so for example, that's 1, 4 there. Okay. Now, because this is a positive y coordinate, okay, that means it's above the x-axis. So therefore, it's going to be positive for all values of x. So therefore, x squared minus 2x plus 5 is positive. This is positive for all values of x. We'll just jot that down there. And there we have it. So we always want to kind of give a quick summary, conclusion at the very end, just to, confirm what we've actually shown there. Okay. And there we have it. So that's our solution to the first example. Now for the next one here, we want to prove that the sum of 3 consecutive even numbers will also be even. Now, let's just think of a very basic example here. So if I pick 2, 4, and 6, so 2, 4, and 6, well, this would be 3 consecutive even numbers, clearly. Okay, 2, 4, and 6. And if I add them together then, 4 plus 6 is 10, plus 2, that would give me 12. So 12 is even. So clearly it works for that example, but how do we show this, or how do we show that this works for every example? Okay. Well, I need to think about this algebraically now. Okay, so how do we represent an even number algebraically? Well, I'm going to use 2n there to be my first even number. Okay, so 2n is my first even number. And we know this is even because it's got this 2 here in front. So we're doing 2 times any number, which would be a multiple of 2. So we know it's going to be even. Okay, so my next even number from here must be 2n plus 2. Okay, it won't be 2n plus 1. That would be an odd number. We'd just be adding 1 to this even number here. So therefore it would be odd. So I've got 2n plus 2. And in that case, my third consecutive even number here would be 2n plus 4 there. So now let's add these together and see what we actually get here. So 2n plus 2n plus 2 plus 2n plus 4 there. Okay. Collect like terms here. 2n plus 2n plus 2n, that gives me 6n. And then I've got 2 plus 4 giving me 6 there. Okay. So we get 6n plus 6. And we need to show that this is even. So again, just like we started with here, okay, with this 2n, if I can factor a 2 out here, it's definitely even. Okay. So we can definitely factor a 2 out here, get 2 lots of 3n plus 3 there. Okay. Because this is something of the form 2 times n in this case, or where n is 3n plus 3 in this case. Hopefully that makes sense. So it's definitely going to be in the 2 times table, and therefore as a result it will definitely be even. Okay, so therefore this will be even. So it's 2, how do I explain this? Multiple of 2, multiple of 2, so will be even. Okay, And that's all we simply need to say there. Okay. And there we have it. So that gives our solution to the second example. So now it's your turn. So have a quick go at these two practice questions. We'll take a look in a moment at what you should have got. So hopefully you got an okay with these two practice questions. Let's take a look now at what you should have got. Now for this first one, I want to prove that 2n plus 4 all squared minus n plus 2 squared is a multiple of 3 for all values of n. So where I should start here really is just by expanding these brackets. Well, 2n plus 4 squared, so that's 2n plus 4 times 2n plus 4. Expanding this using FOIL, I'm going to get 4n squared. 2n times 4, so that give me 8n, and then we do it again here. So it's 4 times 2n, so I get 2 lots of 8n. That would be 16n. And then finally we've got 4 times 4, which gives me 16. Okay. Now we subtract this bracket here squared, so minus n plus 2 times n plus 2. Okay. Well, n plus 2 times n plus 2, again, just expanding this using FOIL, n times n is n squared. So I'm going to do minus. What I'm going to do is I'm just going to put all this in a bracket for now, so that's n squared. I've then got n times 2, so that's 2n. And then same again here, I've got 2 times n, so that's 4n in total. So that's plus 4n. And then finally, 2 times 2 is 4. What I need to do here is subtract each of these terms off. So I've got 4n squared plus 16n plus 16 minus n squared minus 4n minus 4. Now, simplify this here. So 4n squared minus n squared, that would give me 3n squared. We get 3n squared. I've then got 16n minus 4n, so it would give me plus 12n. And then finally, it's 16 minus 4, and that would give me 12. Okay. So how does this show that this is a multiple of 3 for all values of n? Well, can we factor a 3 out here? Yeah, of course we can. So I can factor the 3 out here. We get 3 on the outside. I'm going to get n squared plus 4n plus 4. Okay, so therefore 2n plus 4 all squared minus n plus 2 all squared is a multiple of 3. So this is a multiple of 3 for all values of n. And there we have it, so that's our solution. So generally when you're showing something that is either even or it's a multiple of a certain number, the idea is that we want to factor that number out. So if it's even, we want to factor 2 out. And if it's a multiple of a certain number, we want to factor that number out. Okay, just like we can see we did here. So moving on to the final one here, we want to disprove by counterexample that if n is prime, n squared plus 3 is also prime. Now for disproof by counterexample, the idea here is we just need to find one example where that is not true. If you can find one example where it's not true, then the proof falls apart. Okay, it's definitely not true in that case. So what I need to do is just pick n here, where n is prime, put it into this expression here, and see if that's also prime. If it's not prime, then we've disproved it by a counterexample. So the first prime number here would be n equals 2, our only even prime number. So I substitute that into n squared plus 3. So we get 2 squared, which is 4, plus 3. Now that's 7, and remember 7 is a prime number, so it does work for n equals 2. Okay, so when n is prime, which is in this case, this is also prime. So that isn't a disproof by counterexample because it has proved this statement here. Okay, so we need to try another example. So let's take the next prime number, n equals 3. Then we do 3 squared plus 3. So that's going to be 9 plus 3. So 9 plus 3. And that would give me 12. But remember 12, it's not a prime number. It definitely is an even number. So because it's an even number, straight away we know it's not prime. So therefore, we have now disproved this by a counterexample. So, so n equals 3. So that is a prime number, but n squared plus 3 is not prime when n equals 3. So n squared plus 3 is not prime when n equals 3 there, okay, which is prime. And there we have it. So like I said, with disproof by counterexample, we just need to find one case where it's not true. And we did that there when n equals 3. And there we have it. So that brings us to the end of this video on mathematical proof. In the next video, we're going to take a look at methods of proof.